Is Schrödinger's cat dead or alive? The answer is both. In 1935, Austrian physicist Erwin Schrödinger proposed a nearly absurd thought experiment to challenge the dominant interpretation of quantum mechanics at the time. He imagined placing a cat inside a completely sealed, interference-proof metal box. Inside this small, dark chamber sits a precise and merciless mechanism. A single radioactive atom, a Geiger counter, a fragile glass vial, and a deadly poison slowly swirling within. The entire setup hinges on a tiny chance event. If the atom decays within 1 hour, the Geiger counter detects it, triggering a mechanism that shatters the glass, releasing the poison, killing the cat, all a moment witnessed by no one. But if the atom doesn't decay, the mechanism stays silent, and the cat remains quietly curled up, alive in the darkness. In the world of classical physics, this scenario is simple. You just wait, open the box, and check. The cat is either alive or dead. There's no third option, but quantum mechanics flips this logic on its head. Before the box is opened, the atom state isn't simply decayed or not decayed. It exists in an astonishing superposition. It has both decayed and not decayed at the same time. And because the cat's fate is tied directly to the atoms, the cat too is dragged into this quantum fog. It isn't just alive or dead. It exists in a chilling dual state. It is both breathing and decaying, both alive in a fleeting thought and dead beyond human perception. Even more unsettling, the cat's fate isn't decided by itself, but by an external observer. Only when we open the box, when we look, when we measure, does this ambiguous state collapse into a reality we recognize. And this phenomenon is not unique. Another famous experiment reveals the same quantum strangeness, the double-slit experiment. Scientists fire electrons one by one at a screen with 2 slits. Logically, each electron should pass through one slit like a tiny ball, leaving a matching trace on the detector behind. But shockingly, the electrons interfere with themselves like waves, creating a stripe pattern only waves can make. This means that, without observation, a single electron goes through both slits at the same time, left and right, here and there. But as soon as we observe its path, it behaves like a particle, choosing just one slit. In other words, observation shapes reality. This idea challenges everything we thought we knew. We assumed the universe existed, and we were merely observers. But quantum physics suggests otherwise. We are not bystanders. We are participants, and our consciousness may affect the very structure of the universe. This leads to an even grander idea, the theory of the multiverse. If every quantum collapse defines a choice, then perhaps the unchosen outcomes don't vanish. They live on in other universes. When we open the box, in one universe the cat dies, in another it survives. You take the path to the left. Another version of you walks to the right. Every decision, every observation may split the universe. Reality, unnoticed, quietly duplicates, extends, and unfolds. This world may not be the only one, and that cat might still be staring back at you from another universe. Science has never been just cold formulas. It is a series of breathtaking revolutions in understanding. In Schrödinger's cat, we don't just see a paradox. We face a profound question. If no one looks, does reality still exist?